In this video, we are going to learn how to conduct a chi-squared test of independence. A test of independence is a test that is comparing two qualitative variables, and the information relating these variables is given in a contingency table or two-way table. That simply means we have data that consists of rows and columns. So that gives us two variables, a column variable and a row variable. The column variable is considered to be the independent variable, and the row variable, therefore, is the dependent variable. In this data set, we see that the independent variable is the degree of job pressure felt by workers, and the dependent variable is their age. What we want to do here is test whether the column variable, degree of job pressure, is independent of age, the row variable. In general, the null hypothesis for any test of independence is the row and column variables are independent. The alternative then would be that the row and column variables are dependent. For this example, a more specific null hypothesis would be degree of job pressure is independent of age. And then, of course, the alternative is simply that they are dependent. So we can write here degree of job pressure depends upon age. We are going to use an alpha of 0.025 simply because this is my favorite alpha, as it corresponds to one tail of a 95% confidence interval. So how do we do a chi-squared test of independence? What we're trying to do is see if the frequencies that we have collected, our observed frequencies, correspond to what we would expect, our expected frequencies, under the assumption that the two variables are indeed independent. So that's what we're going to do, is compare observed frequencies with expected frequencies that we will need to compute. This is the basic formula. The expected frequencies are found by taking a row total, multiplying it by a column total, and then dividing by the grand total. Where does this formula come from? Let's go ahead and take a look. And here we are. We want to compute the expected frequencies for each cell in the table under the assumption of independence. Now, if events A and B are independent, the product rule tells us that the probability of their both occurring is equivalent to the product of their probabilities of occurring individually. So if we take our expected or probability under the assumption of independence, we would then multiply that probability times the total to get the actual expected frequency. So the probability of A and B under the assumption of independence would be the probability of A, and so here I am going to consider A a row and to B a column, so we would need the row total for event A and divide that by the grand total, and then we would need the column total for event B divided by the grand total. So the probability that A occurs is the number of ways ways A occurs divided by all possible occurrences, which is the grand total. And the number of ways A occurs is how many are in category A, which is the row total. And the probability of B is the probability that B occurs, which is the number of ways B can occur, which is, of course, the column total for category B, divided then by the grand total, or all possible occurrences. So that's where we get row total divided by grand total. This would be the probability of A, times column total divided by grand total. That would be the probability of B. And that is the probability of A and B occurring, assuming they're independent. But we actually want an expected frequency. E here stands for expected frequency. So we multiply the probability by the sample size, which is the grand total, and this will actually give us the number that we would expect to fall into the cell that corresponds to events A and B happening concurrently. So if we have this formula here, row total divided by grand total times column total divided by grand total, and then multiply that by grand total, we see that one of the grand totals will cancel out, and we're left with row total over grand total times column total, which is equivalent to, right here, row total times grand total divided by, there is a mistake here, it should be row total times column total divided by grand total. So row total times column total divided by grand total is how we would compute an expected frequency. Now, to get good results, it's best that each cell frequency, both in our observed and expected tables, should be at least 5 to ensure that we have a large enough sample so that we have our independence and the application that we're going to use in the chi-square statistics, and all those numbers will come out in meaningful ways. So let's go ahead now and apply this expected frequency formula and find all the expected frequencies. So first, we want to get the number of ways to get low pressure and be less than 25 years old. So the probability of less than 25 years old, or I should say the number of occurrences in less than 25 years old, is 60. So we have 60 who are less than 25, that's our row total, times low, there are 162 individuals with low degree job pressure, but now we divide that by the grand total of 500. Let's do that again. I'll do it one more time, and then I will show you how we can actually copy this. Well, maybe 2 more times, because I want to do for medium, and then I'll do for high, and then I'll show how we can just copy this straight down. So if we want, say, less than 25 and medium job pressure, well, then we will have the same total for less than 25. And now the new total for medium is 170, and we divide that by the grand total of 500 to get 20.4. So notice our first expected frequency was 19.44, and our observed was 20. That sure looks pretty similar. The second expected frequency we computed was 20.4, and the observed was 18. Let's go ahead and do one more using this formula. We want less than 25 and experiencing high job pressure. Divide that by the grand total. 20.16 compared to an observed of 22. Now, when I copy the formulas, I can either copy across rows or down columns. I plan on doing it down columns, that's why I found one for each column. And so we notice here that if we're doing it for low, then the total for the low column will always be there, and we're always dividing by 500. As we go down the column, what's going to change are the row totals, because we only did it for less than 25, so for each of these examples we had 60, but now if we want to do the expected frequency for 25 up to 40, all those 60s would become 140s. If we wanted to do for the age category 40 up to 60, then what we have as 60 would be 180. And if we wanted to do the expected frequencies for the age category 60 and older, the original total of 60 will now become 120. So here we have the color coding, and we see that E11 here, that is the row total. B15, this column total, is always going to stay the same when we are working down the column, and the grand total of 500 always stays the same for every single computation. So I want to fix these two values by inserting the dollar signs, or if I have a PC, I can do the shortcut F4. We'll do that for the grand total as well, F4. So now B15, the total for the column of low degree job pressure, and E15, the grand total, are fixed values and will not change when I copy this formula. But as I copy this formula down the column, here these totals, which are the corresponding row totals, will change from E11 to E12, E13, and E14. So to copy, I put my cursor here to the bottom right, left click and drag, and there we go. And I will click on one of these to show you. So here we are in row 13, all right, with the 180, and there it is, it was copied correctly. Let's do the same for the medium and high columns. So for the medium total will always stay the same. So F4, and then we know the grand total always stays the same. F4, enter, and we will copy this formula. And then we'll do the same thing for high, because now the high total will stay the same. And of course, as always, the grand total stays the same. It's only going to be the row total that changes. So we will copy this formula now. And here we have all the expected frequencies. We're testing independence by comparing the observed frequencies with the expected frequencies. We're going to do that now by finding the difference between those two frequencies, squaring it to make sure it's a positive value, and then dividing it by E to basically get a proportion or a fraction, right? We're looking at the squared difference as a fraction of the expected. The greater the difference, the larger this fraction. The smaller the difference, the smaller this fraction. So we know then that smaller numbers show they are closely related or at least close in value, and large differences show they are far away in value. So let's do that. And this is going to be even easier to write a formula because every cell value will change. So for low, I take my observed low minus my expected low, compute that difference by putting parentheses around it, and raise it to the second power to square it, and then divide by the expected to get this formula here. Notice everything has to do with 11s, B11, H11, H11, and then B and H. And when I move these around, they're actually going to change automatically to then going to H12 or to I13 and etc. So I'll show you this. So we're going to copy this for the entire table, right? So here we have this one. Notice this was high and 60 and older. The observed for 60 and older, 43, minus the expected 60 and older, 40.32. That difference squared divided by the 4.32. So now that we have these individual values, we are ready to find the chi-squared test statistic for this hypothesis test, because that test statistic is found by computing the sum of all these ratios of squared differences relative to the expected frequency. So we just go equals sum, highlight everything in the table, close the parentheses. Notice how when the whole table is highlighted, we have H18, which is the top left cell, all the way down to J21, which is the bottom right cell. Enter, and we get 2.19. That does not look very big. That looks pretty small. We'll find out then if we are right in saying that appears to be small. So what we're doing here, remember, is small to statistics tend to correspond to large p-values, which then support the null hypotheses. Degrees of freedom here have to take into account that there are, in fact, two variables. We have the row variable and the column variable, and so we take one away from each variable, and then we multiply them together. So the number of rows here, 1, 2, 3, 4. 4 minus 1 is 3, times the number of columns, 1, 2, 3, right? Low, medium, high. 3 minus 1 is 2. So our degrees of freedom is 6. And now we are ready to find the p-value. And to find the p-value, we are finding the area in the right tail of the chi-square distribution. So we use chi-squared.dis.rt for right-tailed. So equals chi-squared.dis.rt. First input x is our chi-squared statistic, comma. Second input is degrees of freedom, and that's it. Close the parentheses. So these chi-squared test statistic and degrees of freedom are our two arguments. Hit enter, and we get 0.9. 0.9, 90% of the data, 95% of the data is to the right of this chi-squared test statistic. Let's look at a picture to understand what is going on here. So let us draw. The chi-squared test statistic is a right skewed test statistic, and the tests are always right-tailed. This is a sum of squared values, so everything is positive here. This is a distribution of the O minus E squareds over E. So what we did is we found the sum for ours, which was 2.19, all right? And the values get larger as you move to the right. So 2.19 is really over here. It's probably even closer to the left than I'm showing. So 2.19, this was our chi-squared test statistic. The way we write chi-squared looks kind of like a big giant X, though, with this little tail coming out of it here. And then, of course, we square it. So here's our chi-squared test statistic. Okay, was 2.19. The p-value is the area in the tail defined by that test statistic. So all this area here is the p-value. And we saw that that p-value is 0.90. Very large, all right? So we could easily get this chi-squared statistic by chance, because there's a 90% probability that we would get a 2.19 or greater under the assumption that the row and column variables are indeed independent. So what we have here is a fail to reject the null hypotheses because the p-value is greater than alpha. The p-value is greater than alpha. So remember, alpha was 0.025. Any alpha is going to be less than 0.9. So when the p-value is greater than alpha, we fail to reject the null hypothesis, which means then that we do not support that they are dependent. We have to stick with they are likely independent. And so we say the sample data support the null hypothesis that the row and column variables are independent. Basically what we're saying here, i.e., in other words, degree of job pressure is independent of age. So there's our conclusion. Independence is supported. What possible type of error might we have made? Well, we supported the null hypothesis. So since the null hypothesis is supported, we have a possible type 2 error. So remember, type 2 error is supporting the null hypothesis when it is actually false. So this concludes how to conduct a hypothesis test for independence. And that is when you are testing the independence of two qualitative variables from a table. So here, degree of job pressure and age, the number in each category. Thank you for watching. I hope this was useful.